Hi there, Dr. Fox here again in lesson 10 of this series of lessons for the AQA A-level physics, astrophysics unit. We've got to the stage where we're entering the last part of it, which is basically summing up everything to do with supernova, neutron stars, black holes, and then on to cosmology afterwards, and then a little bit on exoplanets, which I think is a brilliant addition to the specification. It's often you hear a teacher say that really is good because it's proper physics stuff. And it's a good piece of physics for working out what's going on and answering some of the biggest questions. But today we're going to talk about supernovae. I'll talk a little bit on neutron stars and black holes. We're going to save that for another lesson. Mainly because supernovae are a very good standard candle to be able to work out determining distances, and also this idea of concerning the once was a controversy of the expanding accelerating universe and dark energy, but it's not so much a controversy anymore. And how that was worked out by a group of astrophysicists on the two teams. It was a really good piece of science, and I think that's really appreciated. In the specification, they always say appreciate this. I wish in this one there would be the word appreciate the fact that the great science that was done, and it was confirmed, even though it was against everything that astrophysicists had learned up until that moment. So we're going to deal with supernovae, the two different types, and also the products, neutron stars and black holes, but I'm going to save black holes for another lesson. So I'm just going to be dealing with a few bits of this. So basically, the defining properties of these. I'm also going to deal with the supernovae as part of standard candles. A little bit of this, a little bit of that, but then I'm going to save the other stuff about supermassive black holes for elsewhere. Otherwise, we start getting a bit muddled with what we're talking about. So we'll do supernovae first. Again, here we go. In some other things from the specification here, like absolute zero, nuclear fission reactor, just in case you're at a place where this astrophysics unit is taking place at the end of your course. So therefore, you might want to just do a little bit of recap on those as well. What do you do here? Just pick three of these and draw it. Draw everything you know, write everything you know about them in quick succession. So get your notes out, supernova and standard candles. Just one learning objective here to be able to explain the light curve of supernovae. So that is type 1a and 2, which I'm going to talk about, and how they're used in measuring the expansion rate of the universe. And also the difference between type 2 and type 1a, which is what we're going to talk about, which is the most important one, and how they've helped astrophysics over the years work out an awful lot of things about the universe. So type 1a supernova and type 2, I'm going to compare them. So type 1a supernovae are very specific. They come from a binary system, and that's a system where you've got a white dwarf in very close proximity to another star. It could be any sort of color, any sort of star it is. And this white dwarf is accreting material off this other star. And it's an incredible thing, incredible bit of space. And to work out, this is an artist's impression we've got here. And it accretes so much material, it gets to a point where it cannot support itself anymore. White dwarfs are called electron degenerate. They're basically like a huge metal, delocalized electrons. That's not quite true, but imagine it like all the electrons are all delocalized. And it gets to a point where it cannot support itself anymore, and it will then crush down into what's called a neutron star, and effectively becomes the density of a nucleus rather than the density of an atom where you got delocalized. And it's still very dense, but nevertheless, neutron stars are the density of nuclei, which are incredibly dense. And this always happens at the same mass. It's called the Chandrasekhar limit. Go and read about Chandrasekhar and his theoretical physics that worked out this limit, and of course the absolute travesty that he wasn't accepted in the community for very, very many years, and only had recognition afterwards. Go look at the Chandrasekhar limit if you want to look about it. Go and read the story about Chandrasekhar. Fascinating astrophysicist, and depressing history, by the way, around it. But that's the limit it goes down. So it always happens at 1.4 solar masses. So therefore we know that exactly the same mass is involved. Therefore we know that the amount of energy that's involved is exactly the same in every single type 1a supernovae. That means the magnitude is exactly the same. The peak magnitude is exactly the same in every single circumstance. And here we go. We've got supernova going off in a galaxy here, and you can see it's not there, and then all of a sudden it is. You might think, oh, it's a bit poxy, but remember, this is a whole galaxy. So this is kicking out light in the almost like millions and billions of star outputs. And there's roughly a billion or so stars in a typical galaxy. and it all of a sudden gives out the light of almost an entire galaxy in a few months, a few hundred days. It goes through its peak in about 10 days and then tails off and takes a few hundred days to do that. So that's a Type 1a, very specific binary system, gets to the same mass, squashes down, boom, an awful lot of energy is given out. Now, Type 2 supernova is just a single star, usually a very large star, that involves the use of all of its fuel. It gets to a point where it can't fuse anymore. Iron is the limit. If you've done the unit on binding energy per nucleon, you'll know that iron is at the peak of that. If you haven't done that, wait and see. You can't fuse two ions together to make more, to produce more energy from fusion in the center of stars. It just doesn't work. So you end up building up a non-fusing core, and it gets to a point where everything, all the outer layers collapse, and you get this huge explosion of all these different elements fusing together, producing the whole range of every single element that we have in the periodic table, bar a few that we've made on Earth. And therefore, you've got all of this light coming out. And you can see here, this is a supernova that went off a little bit closer. You can see the brightness indifference here. And it's generally this. This is a Type 2 supernova. Variable magnitude of those stars. So they're variable. And sometimes they're in the center, they produce black holes, and sometimes they produce neutron stars. The larger the star, the more likely it is to produce a black hole. With a neutron star, it's a smaller mass star. Of course, Type 2 supernova can also exist in this star in a binary system as well, and sometimes that happens. And that's the reason why you've got a white dwarf here. Small, lower mass stars like the Sun do not go supernova, they tend to just blow off their outer layers. But for this part of the course, we just do them in two sorts. Type 1a supernova, fixed magnitude. Type 2 supernova, non-fixed magnitude. Type 2 supernova, not interested. Type 1a supernova, we're interested because we can use the standard candle. And this is called a light curve. This you need to remember. This is an examinable curve. So up the y-axis, we've got absolute magnitude. Hidden behind my arrow is minus 20. Remember, more negative, brighter. Time days. So it peaks roughly at 10 days and then tails off over about a year, so hundreds of days. And the magnitude is always at minus 19.3. The absolute magnitude is always minus 19.3. Peaks 10 to 20 days, and then it always then tails off after that. And how can these facts be used? If we know the absolute magnitude and we measure the apparent magnitude, we can get the distance from our lovely equation that we did right at the start, which is little m minus big M equals 5 log d over 10. D is in parsecs. So if you've got m and m, which we will have, not the wrapper, that means that you've got minus 19.3 as your big M. Just got to measure your m by looking at the galaxy, looking at the supernova that's gone off, as long as you catch it at its peak. And you can work out where that peak is, of course, because how it goes. And then, therefore, you've got a distance to it. Brilliant. And that means you can work out how far the galaxy is away from it, and that gives you an absolute measure of distance to the galaxy. And that was very important when we determine distances to galaxies, when we're dealing with things like redshift and how we determine the Hubble constant, which I'll come on to later on. So this is basically Type 1a supernova in cartoon form. You get a normal star orbiting a white dwarf. This star starts to expand. The outer parts of it start to be drawn onto the white dwarf, and it gets to a point just hidden behind my head here where the white dwarf goes bang at the Chandrasekhar limit, and then it produces a neutron star after that. But in the process of producing a neutron star, it will release an awful lot of energy. So, just like I said before, why are standard candles useful? Because we can measure things. We can measure the distance to things. Now, Hubble, way back at the start of the 20th century, worked out that there was this relationship between the distance of a galaxy and how fast it appeared to be receding. In other words, he measured the Doppler shift. The wavelength of light was shifted towards the red as he looked further and further into the universe. But the only way he got the distance to this galaxy was by use of something called CP variables, which have a distinct variable output. They pulse, these stars pulse on a certain rate, and that gives you the intrinsic absolute magnitude, the intrinsic luminosity of the star. But he also used Type 1a supernovae as well. Type 1a supernova are particularly useful because they're brighter than individual stars. The using CP variables was only possible in nearby galaxies where you could discern individual stars in them. When you get to very distant galaxies, you end up having a big problem in that you just can't discern individual stars, and you couldn't work out these CP variables and RR Lyrae stars as well, which are the other type of star that was that pulses. So therefore, there was that one way. So there was Henrietta Leavitt, which was the name of the astrophysicist who worked out. She worked out that the relationship between luminosity and the pulse rate of CP variables, and that was useful. But actually, it started to get to a point where you couldn't really do it after a certain distance. But Hubble worked out that this was a linear. You can see this is a linear plot. They're following a pretty tight one with quite a bit of variation. The error on this Hubble constant here, which is the slope of this line, the gradient of this line, it says 71 here, but you'll notice in your formula sheet it's a different number from that. He says from memory, it might be 65 in there. It doesn't really matter. The variation is quite great, and there's a good reason for that, which I'm going to come on to in a second. But just before, just notice these units here. This is the unit of the Hubble constant, kilometers per second per megaparsec. That is a dog's dinner of units. It actually turns out just to be an inverse time unit, because you can see you've got a distance on the top here and a distance on the bottom. If you inverse the Hubble constant and get everything in SI units, it will give you a good measure of the age of the universe, which of course turns out to be about 13.6-ish billion years old. And therefore, it follows this linear plot here. There's no intercept, but there's a problem. There is a problem. When you started looking at galaxies that are a long way off and using the Type 1a supernovae, that means you can look at galaxies that are much, much further away than Hubble could ever have dreamed of with his 100-inch telescope on Mount Wilson. So these two teams did. They measured very high distance. It's called high redshift, but it's very high redshift. But also they measured the distance to them as well, and they discovered that it didn't follow the line. It was above the line. That meant that the galaxies were accelerating. They weren't going at a constant velocity. The universe itself appeared to be accelerating as you look further away, and this was a big surprise. Of course, if you have an acceleration, you need an energy input, and that energy input must be coming from somewhere. They couldn't see it. There's definitely energy, so they gave it the name dark energy. Just like with dark matter, we've tried to explain the fact that there's some matter somewhere but we can't see them. Dark energy is there's some energy but we can't see it, and it is very difficult to explain. There is some residual energy within the universe which is driving the expansion of the universe. Just to put this into context, it's not the galaxies that are being driven, it's the space between them that is expanding. Really important point there. So the universe is being driven, not the galaxies, not like somebody pushing those galaxies. The universe is starting to accelerate at high redshifts, at high distances, which is still a point of interest and a point of controversy. Your job is to be able to explain the line of argument from having a standard candle to supernova type 1a minus 90.3, so therefore that's its magnitude. From the magnitude you can get a distance, you can measure its redshift, in other words measure how much the individual lines, it could be absorption lines, could be hydrogen bomber absorption lines observed, how much they've shifted to longer wavelengths in the spectrum, plotting that just as that graph you have there and seeing what the fact it is. And that is a very, very typical 6-mark question, which will ask you to explain how type 1a supernovas are used as standard candles to be able to give the result that the universe is actually accelerating. Oh, and look, there it is, 6 marks. Type 1a supernova, expansion, explain why observations of supernova led to the conclusion the universe is expanding, and why this conclusion is controversial. Controversial because it needs an energy source, and that energy source is not known. This is an old question, by the way, but nevertheless, it's still one that definitely sits there really neatly within the specification. It's a good one that you can do. And there you go. That's how you answer this. Make sure you include the fact there's absolute magnitude of known. It's a standard candle. You can use the inverse square law, all the values from absolute magnitudes to be able to work out the distance to it. These supernovae are bright, so they can be seen from a long, long way away. These supernovae also existed when the universe was young, so therefore you've got a handle on what was happening in the past. You need to measure the redshift, of course, which is measured of velocity, and these supernovae turn out to be fainter than we expected. In other words, they're further away. The universe has stretched more than we expected. So the universe is expanding faster, and therefore that needs explaining with the type of energy. So there you go. There's your standard one. Pause the video, go away, look at that, write it in your own words, get those points. If you want to do 1, 2, 3, 4, 5, 6 points, that's fine. Do it that way if you remember it. But remember, when you're in the exam, please don't bullet point it. Do it as continuous prose. Examiners love it. It's continuous prose. Here's another one. So there's a light curve. You can see there's definitely a type 1 supernova because it has its peak there as minus 19.3. Time in days along the bottom here. Again, the typical one. Can we use standard candles? Only 2 marks here, of course. And there we are. Go through the idea of it being a standard candle, and therefore you get a standard candle. You need to use the equation. Peak value of the supernova was 12.9 when observed, because it's the apparent magnitude. Using this measurement and information, calculate the distance. Great. So you can measure that value off there. 12.9 is used, and therefore use your n minus m equals 5 log d over 10. Why is it important for astronomers to have several independent measurements for determining the distance to galaxies, just in case of error, just in case of absolute. Anyway,